Hello friends, I am Amirano Nizami and today we are going to see the derivation or the governing equations for Euler-Bernoulli beam using the total potential energy approach. So in the last class we have got the governing equations using the principle of virtual work. Today we are going to see using the total potential energy. Okay, so let's start. So what we know about the total potential energy? Total potential energy. It is the sum of the strain energy stored in a body, strain energy stored plus the work potential or the negative of the external work done. Yeah, so work potential. Okay, generally we denote it with the this pi. Total potential energy equals to strain energy plus work potential. So strain energy, what is the strain energy? Basically strain energy we refer with half times volume integral stress into strain, okay, and volume. So if we write dV, okay, and then what is the work potential? Work potential is the negative of the external work done. So external work done of a beam, what would be the external work done? Let us say, so the work done would be integral, okay, so integrate from x0 to L, and then the load of q of x into the corresponding displacement ws dx. Yes, and here it is volume integral. That is the total potential energy. Okay, so first of all we will write the first part. We will write. So let us see, that is the strain energy, and let us write with the strain energy SE equal half of volume integral. Volume integral means x, y, z. So already we have seen that along the y direction, if we have the integration, so width b is there. Okay, so we have now integration of x and z. Okay, and then we have sigma xx, because here only one stresses, sigma corresponding the stress is epsilon xx, and then dz dx. Okay, now what is sigma xx and epsilon xx? If we remember, for the Euler-Bernoulli beam, what is the displacement field we have? We have u of x comma z equals to minus z times del w naught by del x, and this is only possible when there is only transverse load. If there is any axial load, then we have to include the u naught of x also. Okay, so right now we are not talking about this. We are not adding any axial force. We are just talking about the transverse load on the beam. Okay, so u of x comma z would be minus z times del w naught of x by del x, and w of x comma z we know that is only the function of x, w naught of x. Okay, so what is the strain now? Epsilon xx. So strain is del u of x comma z by del x, and if we differentiate, what will we get? It will be minus z times del 2 w naught of x by del x square. Second derivative would be there. Okay, and what is the sigma xx? If epsilon xx is there, what is sigma xx? Sigma xx is what? E times epsilon xx. Okay, so what we write here, d by 2 x integral z integral, and sigma xx is what? E Young's modulus times strain, so epsilon xx. So it would be epsilon xx square dz dx. Okay, now in the next slide, let's see what is that. X z outside is b by 2. Okay, and E was also there. Let us see, E was also there, which is a constant Young's modulus, so we will keep it out. Okay, be, and then sigma is now epsilon xx square dz dx. So epsilon xx square. So what is epsilon xx here? Let us see. Epsilon xx is what? Del u by del x, which is this, minus z times del 2 w naught by del x square. So we can keep here minus z times del 2 w naught of x by del x square whole square dz dx. Okay, now we can write be by 2 integral, and what we do, we just separate the z integral. Okay, so there would be, if we square here, we will get it plus only, so z square dz. Okay, and that is from where minus h by 2 to plus h by 2. Okay, and here it would be the integration from 0 to L, and that is the integration of del 2 w naught of x by del x square whole square. Okay, because here it is power 2, so we will have whole square dx. Okay, and if you integrate, we have seen previously that it would be z cube by 3 and then h cube by 8 and plus h cube by 8 to h cube by, so we will get finally be by 2 into this one would be bh cube by h cube by 12. Yes, and this rest would be there, x equals 0 to L del 2 w naught of x by del x square whole square dx. So finally what we get, so be, and this is h cube by 12, so b h cube by 12, what it is, we have I, that is second moment of area or moment of inertia, so we can write ei by 2 then integral x del 2 w naught of x by del x square, it is w naught, okay, and whole dx. So we get the strain energy, and we write it separately, that we get E into I by 2 integral x 0 to L, what is that, del 2 w naught of x by del x square whole square dx. Okay, now what is the work potential? That is work potential, we write W, or let us say work potential WP. So that is negative of the work done, external work done. The external work done is Q of x into W naught of x, yes, dx. So now the total potential energy what we have, it is also from x0 to xl. So that is sum of the strain energy, that is Ei by 2 integral x 0 to L del 2 W naught of x by del x square whole square dx minus x 0 to L Q of x W naught of x dx. Okay. Now we got the total potential energy. This is the total potential energy, sum of the strain energy plus work potential. Now what to do? To get the governing equation, what we have, we know there is a term minimization. Minimization of the total potential energy. Total potential energy. Potential energy. It is also referred as first variational principle. First variational principle. What it is, if we make the minimization or use the first variational principle, it will give us the force equilibrium equations, that is called the governing equations of beam. Okay, or Euler-Lagrange equation, Euler-Lagrange equations. Okay, so what we will do, we will write del 1 of the total potential energy. It is called the minimization of first variational principle. Okay, del 1 pi, that must be equals to 0. Okay, that is called the minimization. Okay, so now what to do here, if we have this del 1 of pi, then this would be minimized. Okay, this must be minimized. Okay, so to do it, what we will do, we'll write here, we are directly doing it, Ei by 2 multiplied by, and if you minimize it, so what is that unknowns, that is the W naught of x, so it will go inside, so this 2 power would come out, and it would be like this, 2 into del 2 W naught of x, just like the chain rule we have the derivative, it would be behave like this, multiplied by the del 2 delta W naught of, that is the del x square. Okay, or dx minus the second part is what, x equals to 0 to L, and the work done is Q naught of x into delta of W naught of x dx. Okay, these two will get cancelled, and now if you see what we got just the same as what we were having from the principle of virtual work. Okay, we got the same equation. Okay, and now we take the, let us say 0 equal Ei integral x, what we have, del 2 delta W naught of x by del x square, del 2 W naught of x by del x square whole dx, okay, minus q of x into delta W naught of x dx. This is x equals to 0 to L, 0 to L, okay. Now, what at this point, what we have to do, what we should do, let us see. We have already discussed these things in principle of first order. We got the same equation, okay. What I told, where I told that the finite element method we will use at this stage. So just the same way, here you see this is the what variational part is there, okay, and here it is independent of that. So we have to make this part independent of the derivative. Yes, independent of derivatives. Okay, so how many times we have to apply the integration by part? We will apply 2 times. Apply 2 times integration by parts. 2 times integration by parts. Integration by parts. Okay, so the same step you can see my previous video, and there you will find that how I have done each steps, and then finally we get this with 2 different boundary values, okay, and BC1, BC2, and then we finally get, after the integration, we get the del 4 W naught of x by del x to the power 4 minus q of x, okay, inside the integration, okay, integration 0 to L, and outside is delta W naught of x, okay, that is equals to 0. So now what we do, we say that this cannot be 0, because if the displacement, transverse displacement is 0 itself, then at any point or general points in the beam, so there is no load acting. If there is no load, means no need of analysis. So this cannot be 0. Okay, so what is the possibility that this should be equals to 0? So this entire inside the bracket should be 0. So del 4 W naught of x by del x to the power 4 should be equals to 0. So on the right side, if we write, we will get this governing equation. Okay, so this is the governing equation. Finally, we get the, so this is the third method. Okay, the first method we discussed the direct method. Second, we have discussed the principle of virtual work, and third, we have discussed the total potential energy approach to find the governing equation of the beam. And now, inshallah, in the next class, I will try to solve some problems related to this, okay, using the code. So MATLAB and Mathematica code I will use for that, and then I will show some analytical results, and then we will move to the finite element method, inshallah. Okay, closing here. Thank you.